Okay, guys, here we go. Lecture 7, talking about the fundamental theorem of calculus. So in the last lecture, you learned how to approximate the definite integral, which represents area under a curve, using Riemann sums. And that very last example that we did showed you how to find the exact area under the curve. Well, what I didn't show you is how to actually find that limit that we wrote down in example 5. And to be honest with you, it's a very tedious process and not something that is very much fun. And so because of that, the mathematicians way back tried to figure out an easier way to find the value of a definite integral without having to compute the limit of a Riemann sum. And what they found was absolutely just the most beautiful theorem in calculus, which brings together the concept of derivative and integral. So that's the fundamental theorem of calculus. It says the function is continuous on a closed interval from a to b. Capital F is an antiderivative of f on the interval from a to b. Then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. And so basically, in order to use the fundamental theorem of calculus, you first have to find an antiderivative of f and then evaluate that antiderivative at the upper and lower bounds. Okay, so guidelines for using the fundamental theorem of calculus: provided that you can actually find an antiderivative of f, which is not always possible, you now have a way to evaluate a definite integral without having to calculate that ridiculous sum or a limit that we found in the last lecture. Now, when applying the fundamental theorem of calculus, the notation that I'm going to use is the following. So let's say, for instance, I have the integral from 0 to 3 of x to the 4th dx, just for example. Well, the antiderivative of x to the 4th, remember from a previous lecture, is 1/5 x to the 5th. I'm going to draw a vertical bar here with a 0 at the bottom and a 3 at the top. And what that means is I'm going to evaluate from 0 to 3 and then plug in using the fundamental theorem of calculus. Sorry, that should be a 5. Okay, and it is not necessary to include a constant of integration in the antiderivative like it was when we did indefinite integrals back in lecture 5. Okay, so example 1, we want to evaluate the definite integral. So the first thing I have to do is I have to find an antiderivative of the function. So in this particular case, the antiderivative is going to be x cubed over 3 minus 3x, and I'm going to evaluate that from 1 to 2. And so if I plug in 2 first, that's going to be 2 cubed over 3 minus 3 times 2. Okay, and I'm going to put that in brackets just so that I know that those two terms go together. And then minus, from the theorem, bracket, I'm going to do 1 cubed over 3 minus 3 times 1. And if you calculate that, you're going to get negative 2/3. Okay, so find an antiderivative, plug in the upper bound, subtract, and then plug in the lower bound. Okay, well, in example B, in order to find the antiderivative, the first thing I need to probably do is rewrite this as 3x to the 1/2 dx. That way I know how to use the power rule. And so this is going to be 3 times 2/3 x to the 3/2 evaluated from 1 to 4. And if you want to clean up those constants before you plug in 4 and 1, I would recommend that. And so this would be 2x to the 3/2 evaluated from 1 to 4, which is going to equal 2 multiplied by 4 to the 3/2 minus 1 to the 3/2, which if you calculate it is going to be 14. Okay, now you do need to be able to do that without a calculator, so let me maybe just talk about how to do this 4 to the 3/3 term, okay, without the use of your calculator. So maybe back up here, 4 to the 3/2. Well, in order to do that, what you could do is you could cube 4 and then take the square root of it. Well, that's honestly not too hard in this case, but sometimes when those numbers get large, you're not exactly sure what to do, and they get too big that you just don't know them without a calculator. So instead of cubing 4 first, take the square root of 4 first, and then raise it to the 3rd power. Okay, so in that case, 4 to the 1/2 is 2. And if you cube it, you're going to get 8. So that's how I got 8 here, minus 1, which was 7, and then multiplied by the 2 gave me the 14. Okay, so just make sure that you can do those basic arithmetic things without the use of your calculator. Okay, example C, we need to find an antiderivative of secant squared x dx. Well, my derivative rules, my knowledge of derivatives should help me remember that tangent x has a derivative of secant squared x. And so in this case, the antiderivative is going to be tangent x, evaluated from 0 to pi over 4. Okay, so if we plug in our upper bound first, we're going to have tangent of pi over 4 minus the tangent of 0. And in order to get this problem correct, you have to know the unit circle. So that's why I gave you assignment 0 to help your unit circle skills. Tangent of pi over 4 is 1. Tangent of 0 is 0, and so the answer to that definite integral is just 1. Okay, part D, the integral from 1 to e of 1 over x dx. You should hopefully recognize this as being the same thing as x to the negative 1 dx. And if I try to bump that up and divide, I'm not able to do it because it increases to 0 and I can't divide by 0. So that should hopefully make you remember that this is a different rule. And in this case, it's the natural log rule. So ln of the absolute value of x evaluated from 1 to e is going to equal the natural log of e minus the natural log of 1. These are also two values that you need to have memorized coming into calculus. And so natural log of e is 1 and natural log of 1 is 0. And so the answer, again, is 1. Okay. Now we want to use the fundamental theorem with the substitution method that we learned in Lecture 5. So in Lecture 5, you learned how to use integration by substitution to evaluate indefinite integrals. And the substitution method is really just an advanced way of finding an antiderivative. So we can use the substitution method on definite integrals as well if it is necessary to find an antiderivative. So remember, when you're using the substitution method, you're looking for two things. A function that is inside of another function whose derivative is somewhere in the problem up to a constant. Okay, so example 2, we want to evaluate the definite integral from 0 to 1 of x times x squared plus 3 squared. Okay, well the reason I know that this is a U substitution is because I see a function inside of another function. And so I'm going to choose that as my u, and so u is going to equal to x squared plus 3. That means that my du is going to be 2x dx, and I see x dx in the problem. So I'm going to divide by 2 in order to get the x dx by itself. Okay, so if I start putting back together this integral, I'm going to have 1/2 and then du at the end. Integral sign is going to stay an integral sign, and then I'm going to have u to the second power. And then the last thing, and this is different from Lecture 5, so this is the new thing that we're introducing here in Lecture 7, is that I have to find some way to replace those bounds right there. Those bounds are in terms of the variable x. We have now shifted everything to be in terms of the variable u. So what I have to do now is I have to replace that 0 and that 1 with new bounds. And so what I'm going to do is I'm going to plug in that 0, which is the original lower bound, into my equation for u, which is back up here in yellow, and I'm going to figure out what the new bound is. So that's going to be 0 squared plus 3, which is equal to 3, and so that's going to be my new lower bound. And then my new upper bound is going to be u of 1, which is going to be 1 squared plus 3, which is equal to 4. Okay, now that I am here, I'm going to do this in a different color. Now that I am here, this is the problem that I am now trying to solve. This problem is now completely irrelevant. So everything to do with x just kind of goes away, and now I am trying to solve this problem, 1/2 the integral from 3 to 4 of u squared du. Okay, so if I do that, I need to first of all find an antiderivative. So I'm going to write the 1/2 that came from right here. That just gets copied down. And then the antiderivative of u squared is 1/3 u cubed, evaluated from 3 to 4. Okay, well this is going to be 1 over 6, and then if I plug in 4 first, 4 cubed is going to be 64, minus 3 cubed, which is 27, and so for my final answer, I'm going to have 64 minus 27, which is 37, and then divided by 6. Okay, so there is my final answer. Now be careful, I want to say this again just to be clear. Once you shift everything to u, you are completely done with x. So these things right here, okay, this original problem, completely irrelevant once you substitute everything into the variable u. Okay, letter B, we have the integral from 0 to 4 of x over the square root of x squared plus 9. So again, I know it's a u-substitution problem because I see a function, x squared plus 9, inside of another function, which is the square root. Okay, so u is going to equal to x squared plus 9. That means that du is equal to 2x dx. And again, I see x dx in the problem right here, so I'm going to solve for that, so that it says 1/2 du is equal to x dx. Okay, so my new integral is going to be 1/2 the integral du down here at the end. And then what's left over is a 1 over the square root of u. Well, instead of 1 over square root of u, I'm going to write it as u to the negative 1/2. Okay, if you have questions on that, then please feel free to let me know. The reason it's negative is because that square root was in the denominator, and the reason it's a 1/2 is because it was a square root. Okay, the last thing I need to do is figure out my new bounds. So u of 0, which was my original bound, is going to be 0 squared plus 9, which is 9. So my new lower bound is 9. And then u of 4 is going to be my new upper bound. 4 squared is 16, plus 9 is 25. And if you're lost as to where I'm plugging that into, I'm plugging that back in right back up here to get my new bounds. Okay, so 25 will be my new upper bound. Now I'm ready to take the antiderivative. So you have to be very careful to take the antiderivative once you get here. So this is going to be 1/2. The antiderivative of u to the negative half is 2 u to the 1/2, evaluated from 9 to 25. The 1/2 and the 2 here are going to cancel, and so what I'm really going to get is 25 to the 1/2 minus 9 to the 1/2. And since to the 1/2 power means square root, what I really have is 5 minus 3, which is equal to 2. Okay, let me know if you guys have any questions on that. On your assignment, all of the problems are going to be mixed together. So some of them will be u-substitution, and then other ones will be easy, like example 1. You have to determine which method of finding the antiderivative you're supposed to use. And the hint that I want to leave you with is look for a function that is inside of another function. If you see that, then it's more than likely a u-substitution problem. Okay, there's also a second fundamental theorem of calculus, and this theorem, this part of the theorem, shows us how to take the derivative of an integral. So hopefully by now you've kind of understood that those two processes, the derivative and the integral, are inverses of each other. And so whenever we take the derivative of an integral, the integral is just going to cancel out. Now that's going to cancel out in kind of a special way here. So I want you to read the theorem. It says the derivative with respect to x of the integral from a, so a is any constant, to g of x, where g of x is any function of x. Could be x squared, could be square root of x, could be sine of x. It really could be anything, any function of x. In order to find the derivative, what we're going to do is we're going to take the g of x, so take this upper bound, we're going to substitute it in to the function f of t. So that's this part of the answer, f of g of x. The g of x just went into f of x. And then we have to multiply by the derivative of the upper bound, and that's because of the chain rule. Now this is something that you need to get comfortable with. We are going to be doing this a ton in the next school year. So you have to be good at taking the derivative of an integral. Okay, so part A here, the derivative with respect to x of the integral from 0 to x cubed of ln of t squared plus 1 dt. Okay, well in order to take the derivative of that integral, what I do is I take the x cubed, which is the upper bound, I substitute it in to all of the t's that I see in the function that we're integrating. So I'm going to do natural log of t squared, but instead of t, I'm going to put x cubed. So x cubed squared is going to give me x to the 6th power plus 1. And then I have to multiply by the derivative of x cubed, which is 3x squared. Okay, so if I clean that up, that's going to be 3x squared times the ln of x to the 6th plus 1. Okay, so don't forget to multiply by the derivative of the upper bound. That, again, is an application of the chain rule. Okay, problem B, we want to take the derivative of the integral from 0 to x squared of sine of t cubed. So this is going to say sine of, I'm going to take the x squared, I'm going to plug it into the t. Since it says t cubed, I'm going to cube x squared, which again gives me x to the 6th, and then multiplied by the derivative of x squared, which is going to give me 2x. Okay, so it's not real hard. You just need to practice it a little bit so that you get comfortable with what exactly you're supposed to do. Okay, and then problem C here is just an application of using the second fundamental theorem of calculus. So it says, let h be the function defined by the integral from pi over 4 to x of sine squared of t dt. Which of the following is an equation for the line tangent to the graph of h at the point where x equals to pi over 4? So we're trying to find the equation for a tangent line. Well, I know that the first thing that I need is a point. Well, it gave me the x value. The x value is pi over 4. That's right there. So to find the y value, I'm going to plug into the original function. So h of pi over 4 is going to be the integral from pi over 4 to pi over 4 of sine squared t dt. Well, remember from lecture 6 that if we have a definite integral whose bounds are equal, then the answer to that integral is just equal to 0. Okay, so I utilize that property here in order to get the y value. Okay, the second thing that I need, I'm going to do that back over here, is I need the slope. And so in order to get the slope, I have to take the derivative of h of x, which is h prime of x. Okay, well, the derivative of that is going to be, I'm going to take the upper bound, which is x. I'm going to substitute it into the t, and so that's going to be sine squared of x. And then I would multiply by the derivative of x, which, of course, is just 1. So that means that h prime of pi over 4, which is going to give me my slope at pi over 4, is really sine of pi over 4 squared. Well, sine of pi over 4, I know, is the square root of 2 over 2 squared. And if I square that, what I'm going to get is 2 over 4, which is equal to a half. Okay, so if I'm ready to write my answer is going to be y is equal to y1, which was 0, so I don't really need to write anything, equals to my slope, 1/2, times x minus pi over 4. So this right here is my final answer. Okay, if you guys have questions or have any problems on the assignment, then please feel free to let me know.